All right. So do you have any questions about the previous work that you just did? The one that you turned in today? If you have questions, you can ask them now. Because the one for today, it might be a little bit easier than the previous one, but it's very related. And one of the reasons that the problem was hard or something, if you want to discuss it, that works right now. If not, I don't see anybody raising their hand. If you have any questions, just raise your hand or speak up, okay? Let's go into the next step. So for the activity for today is a relativistic flyby. So here's what I have in mind. Let's say that you had a spaceship. Oh, to change to pen. There we go. Okay. So you have a spaceship. Ooh, this is horrible. I'm trying a new pen combination and it's not looking pretty. So this is your spaceship, is going in that direction. Okay. He has a window here. So now it looks like a finger moving around. Okay. So your spaceship, let's call it A, is traveling close enough to a space station. So then you will have a space station down here. The space station is located here. It has solar panels on it. So that's what the two things here hanging out are, the solar panels. This is the space station. And it's passing by at a distance close enough to see. And also this guy is moving in this direction. He's traveling fast enough, but it's not accelerating anymore. He's traveling fast enough. It was traveling fast enough so that it doesn't need to accelerate, so it's traveling with a constant velocity in that direction from the spaceship. So now you're the person on duty on the spaceship B, and you see that the length of A, you measured it at 50 meters. All right, so your friend who's traveling on A says that when they got into the spaceship, in this frame of reference, in the frame of reference, when they were getting into the spaceship, it was 80 meters. All right, so here's the first question. When you were on B, what is the speed So what is the speed from the point of view of the space station? Okay, so that's the first question to ask. How do you guys want to do this? Do you want to work it all out in the smaller groups, or I think we're a small enough group that we could all talk about it and how to do it. Any preference? Staying all together here, or you guys prefer to go into little rooms? Anybody? Stay here? All right. So what is the strategy that you guys would take? Anybody? You can speak up or put it on the chat.
So on the 80 meters and the 50 meters, is that like meters per second, or is that their height?
No, that would be the length of the spaceship.
Gotcha.
So when it's traveling, right? So what do we know? We have an equation to relate things. And this equation is the Lorentz transformation, right? The Lorentz factor. So let me write the Lorentz factor over here. And it has 1 divided by, and then here's a square root of 1 minus b squared over c squared. And then you also know, this is something that we covered on the previous one, that delta t in the moving one is equal to this factor times delta t in the proper one. And we also know that the length, if it has a proper length, one that is traveling at a particular speed, the same length. So the length one goes, you know what the proper length is, then you divide it by the factor, and then you get the length of the velocity. So Joshua, yeah, what is the proper length of this guy, of the spaceship?
Is it 80 meters?
Exactly, right? So that's the proper length, because that was the length that somebody inside the spaceship would measure, or if it was at rest and you're in the same frame of reference on it, is the length that you would measure. So now, based on that, now you have to solve for B, right? Now you know which one is the, so you're comparing two frames of references, and you're comparing, and I don't think, oh, I can do it this way. So you're comparing this 80 to this 50. So the 80 will go here and the 50 goes here. So now all you have to do is figure out what is the velocity so that you get that value. So you guys are welcome to try it. I'll give you 3 minutes to do the algebra and then put the equation in. Questions about what you're doing? All right, go for it then. All right, do we have an answer?
I've got about 0.78 C.
0.78 C. So that's the speed at which the spaceship is traveling. Anybody get anything else? I got yeah, close to 0.78. That gives you a little bit above the 50 meters. So if everybody got that same answer, then we're in good shape. All right, so now that's the warm-up question. But the other one is not that much harder. So the second question is, when the crew, in the point of view of the crew, the length of the space station is 200 meters. When doing the flyby, what is in that frame of reference this length that they measured? Okay, go for it.
Wait, so what is LB again?
So length of B is the length of the space station, right?
From
So
the
we
point
have a
of view
space
of the
station.
people on the spaceship?
There's people in the spaceship, in their frame of reference, they measure this distance from here to be 200 meters. The people in the spaceship, they're doing their flyby and they can measure the length of this guy, right? What, since they're traveling at the speed that you found, what is the length that they would see here as opposed to this one? Okay, it's not gonna be too, all right, so first a check question. Should it be bigger than 200 or smaller than 200? What do you guys think? Let me put in a poll. How do I do this? Oh, type your question here. Bigger than 200, true or false? There we go. So you guys can say, should it be bigger than 200 or smaller than 200? All right, so at this point, we have 56% and 56% saying that is bigger than 200. Versus 44%. So it's pretty split down the middle. It's 5-4. Kind of like the Supreme Court, right? 5-4 in every issue. So looking at this equation, which one is the proper length? Is the proper length 200 or not?
Would it be the 200?
And the spaceship is the one moving, right?
Yes.
So now look at it this way. This gamma guy, this Lorentz factor right here, if the speed is 0, is 1. So that means the speed is 0 is 1. If the speed is, let's say, whatever value you want, 0.1 of the speed of light or 0.5 the speed of light, half the speed of light or whatever, is going to be smaller or bigger than 1, right? What is the minimum value that gamma takes? Is actually 1, because if you go 1 minus a number, it's going to be a smaller than 1, and then you have to go 1 over that is smaller than 1 number. So it's always either 1 or larger, right? Since gamma is bigger than 1, you measure 200 in the proper time scale, in the proper length scale, in the proper frame, sorry. Once you do that, you look at the length of the people traveling at whatever speed it is, at the speed that you put in. Should it be bigger or smaller now? All right, so let's go. Right, so if this is 200 and this is, let's say, 10, then it's reducing this 200 to something else. So now we have all of the smaller values. All right, so we have a question from Haiti. Can you explain how to get the answer to A? I did not get it. Sure. So let's look at A. What we know is this. So using this equation, right? This equation right here. What you had to do is first, you know that LB is 50, and we know that L proper for the spaceship is 80 meters. So this is 50 meters, this is 80 meters. So then you look at this equation right here, and you can write it out. You have here is the 50 meters, here is 80 meters, and then this gamma factor right here, which is up there, is just gonna multiply it like this, 1 minus b squared over c squared. So now what you have to do is do the algebra, right? So that you square this side, or, sorry, you could even do it easier. I don't know, the algebra. So that means, I mean, there's different ways to do algebra, right? So now you have 50 over 80 over here is equal to this n. And then you can square both sides, get a number out, square this one out. And then that means that you have 1 minus b squared over c squared. And here you have a number. And then you just solve for b. What is this value of b squared? And you get the right answer. So you can grab this one, take it over here, or however you do the algebra manipulation, and that's how you get the 0.78. Yeah, around 0.78. All right, so now for this other approach, we have something very similar. Now you have that the spaceship is measuring the distance. What would they measure? Right? So go ahead and try it. And you can speak up on your strategy. I think that is a very similar, but not exactly the same. Or if you have the answer already, you can tell us what it is. All right, let me give you a couple of minutes to do that. All right, so do we have an answer? 12.4. Do we have somebody else? 125. Okay, perfect. Yeah, it's around 125. So this spaceship that is traveling sees the length of the space station below it to shrink. The people in the space station, when this spaceship is traveling, see that length shrink too. Isn't that weird? I think that that's an interesting thing that unfortunately we don't have ourselves traveling that fast, so we don't get to measure those distances. That's just the way it works. That's actually the reason it is happening is because that's the way the universe works. Those are the rules that were set up and how the universe behaves. It's based on observation. It's not that Einstein made it up, it's just that this is how the universe works. And one of the interesting things is that people didn't understand this or realize this because everything moves so slow compared to the speed of light for us human beings. But there's a lot of proof that this is working in the universe. So for instance, all of the rules that you learn in physics 1, they're not relativistic, right? Like you have the energy, kinetic energy is 1/2 mv squared, and you have memorized this. I'm sure everybody has this memorized. And that 1/2 mv squared, if you're traveling at relativistic speeds could be anywhere like above 5% the speed of light for you to measure this. It actually is not true, and it changes. And the reason for that is because it depends on special relativity at that point. So I think it's a good time right now to take you back to some of the things that you have learned already. So we know about time measurements, right? Like for instance, we know what is an event. We know what an observer has to do to measure when an event occurs in a reference frame. And also that just because two people make a measurement, it doesn't, and one of them might think that it's simultaneous, and he's right, for him it's simultaneous. The other person, she might make the measurement at the same time. In her frame of reference, it's not simultaneous. So if you have two events happening, we have also learned this. This is a special relativity, right? That simultaneous is just a relative term. So it depends, simultaneity of two events seen by two observers is not the same. Now we have just covered a space-time, and what we have is the proper length of an object. We understand what proper length means now. We have proper time, so now we have a space and time, both of them together. And with these two activities that we have done the previous 2 weeks, we have a good, maybe not, it's not something that we understand completely, but we have an understanding of how the speed at which something is traveling changes the time measured. So for instance, for the previous homework, the people that were in the spaceship moving at a high enough velocity, the signal that they were getting, they were measuring it at 1 second. And the signal that they were sending out, it was measured at 1 second intervals. While back on Earth, the signal that you get from them was it way faster or way slower? You guys remember? That's the spaceship moving really fast, right? So it has a signal that is coming out, and then you measure it over here. And then you had to send the signal back to them, and you had to send it slower so that these guys that are moving fast could get it at 1 second intervals. So you have an idea of what time dilation is. We use this Lorentz factor to get this. And also when it becomes noticeable to see this. And then we have an idea of length contraction. How when something is moving way faster, it gets shrinks. All right. So we know length measured by the observer, whether they're moving with the object or not, that would change the length that you're measuring. All right, any questions up to here? And I don't know if I answer your question of why does this happen. I mean, it's just the way that it is, right? These are the rules of the universe. It's not the classical mechanics of Newton doesn't work anymore. All right, so then we next want to talk about energy and momentum. So that would be for next class. At this point, if you guys don't have any questions, I'm ready to let you go. And we did the activity for today right here. Maybe you guys need a little bit of a break since you just had the exam. So I'm happy to let you go at this point. Any questions? Any concerns you have, just let me know. All right, so see you all next week. There's no homework, okay?